Good evening, guys. My topic tonight will be the volume of a sphere, and the solution will be integration by using the hollow cylindrical method. Okay, so the topic is still volume. We will apply it to the volume of a sphere, and the solution should be by using hollow cylindrical method. Okay, let's proceed. Lesson number 73 on my channel. The topic is integral calculus. It is under volume, and the subtopic is hollow cylindrical method applied to sphere. We will derive the formula of a sphere by using the hollow cylindrical method. So actually the topic is still hollow cylindrical method of volume derivation. And we will apply this hollow cylindrical method on a sphere. We will derive the formula for the volume of a sphere as a function of its radius. And actually the final formula, guys, volume is actually 4/3 pi r cube. We derived this formula when we were in the topic, what do you call this, circular disk method. Okay, we derived this. And again, by using the hollow cylindrical method, again, we will derive this one. So actually, there are many solutions on how to derive the formulas. That's the essence of integral calculus. Okay, let's proceed. The problem is, derive by integration the volume of a sphere using hollow cylindrical method. Hollow cylindrical. Hollow cylindrical is something like this. If we try to rotate the hollow cylinder with respect to the y-axis, it should move like this. Okay, it's a hollow cylinder. Before it was a circular disc. That circular disc, it does not move like that. It should move like this. The rotation is actually different. But for a hollow cylindrical method, okay, if this is the y-axis, it moves like this. It seems it's like just like a cylinder, but it is hollow. That's why the topic is hollow cylindrical method. Okay, let's try to bring out the figure. Cartesian coordinate system, this is the y-axis, x-axis. We drew a circle over here, and for it to look like a sphere, this is actually a curved side, and the back side is actually a curved side also. So it seems it's just like a ball. Okay, so it's a volume. The radius of the sphere is actually r. The radius is r. Okay, let's draw the vertical slice. This is the vertical slice. Okay, this is y higher, this is y lower. Y higher lies on the circle, okay, and y lower lies on the horizontal axis. Okay, the thickness is dx, and the distance of this thickness from the axis of rotation. The axis of rotation is actually the vertical or the y-axis. Its radius, its distance from the axis of rotation is x. Okay, so it seems this is the horizontal slice. The thickness is dx. Its distance from the axis of rotation is x. Okay, and this is actually y higher minus y lower. Then we try to rotate this one complete revolution. So what will come out if we rotate this one complete revolution is something like this. It's a hollow cylinder. The one at the middle is hollow, you know. It's hollow. So this was the thickness of the differential area. as it rotates. The middle part is actually hollow. That's why it is hollow cylinder method. The height is actually y higher minus y lower. It should be the y here minus the y here, as dx moves from this point here up to this. Okay. The height of the differential area is actually variable. Okay, it varies because the circle is not it's not a regular figure. Okay. If we try to cut this one now, what will come out is something like this. The thickness is dx. The one that goes around refers to the circumference. This is 2 pi x. And this length here is actually this. It is actually y higher minus y lower. Let's try to bring out the solution. I will erase this one so it looks great. Okay. Solution. Differential volume, circumference times thickness times height. Differential volume will be 2 pi x times dx. The height, this is a variable height, guys. Variable height. It is the difference of y higher minus y lower. Y higher is the ordinate of the circle, and y lower is the ordinate of the straight line over here. Because as dx moves from 0 to r, okay, this movement is not changing, but the movement of the circle is actually varying. So actually the difference y higher minus y lower as dx moves from 0 to r, it varies. So differential volume now will be 2 pi x dx times y higher minus y lower. So actually, I will try to erase this one. Hold on, guys. Sorry for that one, my eraser fell down. So we are now given differential volume as a function of y higher and y lower. And it should be, what will come out should be a pure function of x. Okay, so we will try to derive y higher as a function of x and y lower also another function of x, g of x. So if we try to substitute y higher minus y lower back here, okay, what will come out will be differential volume as a function of pure x. And if we could bring out the differential volume as a function of pure x without any other variable, we can now proceed with integration to solve for the volume. So actually, differential volume is 2 pi x dx times quantity y higher minus y lower. Okay, let's try to bring out the value of y higher. Y higher is actually the variable ordinate on the circle. The variable ordinate on the circle, the movement is actually variable, okay? That's the movement of y higher, okay? And to get y higher, we should know the equation of this. It is just a circle with center at 0, 0. So x squared plus y squared equal to r squared. So from that, y squared should be r squared minus x squared. Taking the square root of both sides, these two here cancel with this. Left hand side will be y equal to r squared minus x squared raised to 1/2, or this is the square root of r squared minus x squared. I will now place the proper subscript. This is y higher. Equation number 2. This is the variable ordinate as dx moves from 0 to r. It varies. This is a variable thing, okay? And for y lower, the movement of y lower is this. As you can see, it is a straight line. So y lower is actually straight line, and it coincides with the x-axis. So y lower is actually 0. This is equation number 3. The equation of this is y lower equal to 0. And the equation of this, that's it. Okay? Because as dx moves from 0 to r, this does not vary, but the ordinate on the circle varies. That's why if we try to compute for the variable height, it should always be the difference of y higher minus y lower at any moment. So getting equation number 2 and 3, we put it on equation number 1. They should now be 2 pi x. This is y higher minus y lower. This is times dx. I place dx last. Okay. So differential volume will be 2 pi x times the square root of r square minus x square dx. This is now a differential equation. And we are now given differential volume, or differential volume as a function of x dx. Okay, pure x. There are some other function, what you call this, factors inside, but 2 pi is constant, radius is constant. So actually it seems we are given differential volume as a function of pure x. If we try to integrate this one, I don't have ink anymore. I should buy a new one, guys. Okay. Try to integrate both sides. But if we try to look at the figure, we are only taking, rotating 1/2 of the sphere. So this is actually volume over 2. And the limit should be from 0 to r. Okay. If we try to integrate this one, I think this portion is integrable. It seems this is under the power formula. The value of u is actually r square minus x square. du will be r square is pure constant, and the differential is 0. This is minus 2x dx, or du is minus 2x dx. It is not exact. So it seems this is under the integral of u to the n du. Okay. So the integral of differential volume over 2 now will be equal to the integral from 0 to r of 2 pi. Since this is not exact, we will introduce negative 1/2 outside. Okay, negative 1/2 times r square minus x square raised to the 1/2. Okay, then we place the exact differential as per verification minus 2x dx. The integral of differential volume over 2 will be volume over 2 equal to, these two here cancel with this, so negative 1 times pi will be negative pi, right? And the integral of this, it falls under the power formula. This should be r square minus x square. 1/2 plus 1 is 3/2, so this is raised to the 3/2, all over 3/2. Closed quantity with the limit from 0 to r. Okay, what will come out will be volume negative 4 over 3 times pi. These two here will go up, right? So will it go out? Oh yeah, it go out. Actually, these two now goes here. This is minus 2 pi. Okay. So minus 2 pi times 2 will be negative 4 pi. That 3 remains at the bottom. This is over 3. And if we now try to place the upper limit, when x is r, the value of the upper limit will be 0. And when x is 0, the value of the lower limit will be r square minus 0, or simply r square raised to the 3/2. And luckily, these two here cancel with this. So what will come out? Negative 4 pi over 3 times negative, this will be negative r cubed now, r to the 3rd power. So this is negative, it will now be plus. So volume now will be 4/3 pi r. This is r cubed, guys, r cubed. So this is now the formula for taking the volume of a sphere by using the hollow cylindrical method. So as you can see it, volume is still the same. Whatever will be the solution, circular disc or hollow cylindrical method, the required volume for a sphere as a function of the radius is volume 4/3 pi r cubed. This is r cubed. You see, guys? whatever will be the solution, and if we try to derive the volume, what will come out will be the same. So volume for a sphere by using the hollow cylindrical method, volume is still 4 thirds pi r cubed. So that's the significance of integral calculus. Actually, all the formulas under lower mathematics, under solid mensuration, okay, emanates from integral calculus. So actually, integral calculus is the mother of lower mathematics. Okay, good evening, Los Angeles.